Mama kuliah dulu, Ham.
Halo Ibu.
Ibu punten suaranya tidak terdengar. Belum, Bu.
Sekarang ada?
Ya, sudah ada.
Ada, Bu.
Oke, thank you. Ya. Selamat pagi semuanya. Kita menunggu kehadiran Dr. Wenda untuk bergabung bersama kita di perkuliahan visiting professor untuk mata kuliah pengolahan air ya. Kalau yang ada di prodi kimia. Selamat datang juga untuk partisipan dari luar prodi kimia. Selamat bergabung kembali. Hari ini kita akan melanjutkan perkuliahan yang tertunda sebagian ya. Di minggu lalu kita sudah lebih detail membahas tentang membrane technology in term of preparation gitu ya, pembuatan membrannya dan juga characterization-nya gitu ya. Bagaimana teknik karakterisasi yang bisa dilakukan untuk penyiapan membran. Hari ini mungkin Dr. Wenda akan melanjutkan perkuliahan terkait dengan membran teknologi ini untuk beberapa model aplikasi ya. Minggu lalu juga sudah dikupas beberapa contoh itu penggunaan membran material dalam konteks water purification gitu ya. Baik di model reverse osmosis gitu ya, kemudian di ultrafiltration, di microfiltration. Nah, mudah-mudahan sekarang bisa lebih detail lagi. Bila Anda ada pertanyaan gitu ya terkait dengan konten itu saya kira jangan ragu untuk ditanyakan saja di chatroom. Manfaatkan ini kesempatan baik untuk bisa mengeksplor informasi ya, memperoleh berbagai informasi terkait dengan teknologi terkini di konteks pengolahan air ya. Bu Mita, record perkuliahan sebelumnya sudah ada di YouTube atau belum?
Belum, Bu, sedang diunduh.
Oh iya, silakan diambil ya. Mudah-mudahan bisa diikuti. Just in case ada kendala bagi Anda untuk mengikuti perkuliahan sebelumnya, ini bisa diikuti di di recordnya ya.
Kalau yang 2 minggu yang lalu sudah ada, Bu.
Kemudian bagi yang mengambil credit earning, kita memerlukan data lengkap Anda gitu ya. Mohon nanti dikirimkan ke email Ibu Mita saya kira atau email departemen yang kemarin digunakan untuk menghubungi Anda ya. Jadi NIM, kemudian identitas Anda, saya kira dari institusi mana, program studi apa, kemudian mata kuliah yang ingin diklaimkan di sana ya. Kalau sudah ada model konversinya silakan Anda berdiskusi dengan dosen di prodi Anda gitu ya. Yang jelas kami berikan nama mata kuliahnya di sini ya untuk pengolahan air dan setara dengan 2 kredit ya. Silahkan. Nanti mohon dikirimkan gitu informasinya. Mungkin kalau memungkinkan juga copy NIK Anda atau apa namanya kartu mahasiswa gitu, itu juga kita perlukan ya untuk mengurus administrasi di bagian akademik untuk di UPI. Nanti di akhir perkuliahan kita akan siapkan. Baik, nampaknya Dr. Wenda sudah bergabung dengan kita. Very good morning, Dr. Wenda.
Can you hear me right?
Oh yeah, very clear, Doctor.
Okay, sure.
Yeah.
Oh, you're
Good
still
morning.
at home?
Yes.
Morning.
Yeah, still at home. Actually, the temporary close for our office already open, but since the
It's better
activity.
to be at home, right?
Yes, and also I have some duties after this lecture to be conducted at home. Okay, good morning, Dr. Wenda. Very glad to see you again. If I'm not mistaken, last Thursday, I had another meeting with other colleges from Malaysia due to some activities in Jakarta, and he said in Malaysia is quite critical due to the COVID progress.
It's not as bad as in Indonesia.
Yeah, of course, it's not so comparable, but for them maybe it's so frightening, yeah, because
Yes.
the number of cases, he said, almost 3 times higher per daily number, yeah.
Yeah, now we have about 1,000 cases every day.
I see. So almost 3 times, right?
Yes. This is what we call as a third wave. So it's increasing every day, and you know we have a recent election right in Sabah. Right, so because of the election, then all the people who came back from Sabah spread all the virus all over the country.
I see. Yeah, he mentioned also that evidence, due to the election, and also we afraid to see the same evidence here, because in the near future, if I'm not mistaken, on December or something, we would also have the local elections for several regions. Yeah, and as you know, here due to that activity, we mobilize many people to come together and so on. And sometimes everyone just forgot about the protocol, how to prevent the infection. Very worry, due to the many evidence from other countries, from neighborhood, from Malaysia, as well from other countries. So, but I don't know how the government can handle this kind of evidence. Hopefully, we can.
Hopefully it will be okay next year.
Hopefully. Okay, Dr. Wenda, I guess gradually the participants join with us, and very good morning to all students as well as the participants from out of UPI. So today we will continue the lecture, from Dr. Wenda. Still, I guess the content for this lecture is continuing the material that still remain regarding to the membrane science and technology. And after that, maybe some additional information would be delivered by Dr. Wenda. And last week, we really had a very fruitful time, very comprehensive, and also many informative, content, been delivered by Dr. Wenda regarding to the membrane science and technology due to the principle of the membrane science, as well as the technique how to prepare the membrane, as well as the characterization of the membrane. And today, we will have the additional information, as well as knowledge about this topic. So, Dr. Wenda, without any further ado, I guess time is yours. Now you can start the lecture.
Do you need to wait until 9? Because I think it's okay.
You can deliver some introduction or some information that needs to be informed to the student maybe before your lecture. Here in my clock is 7:58, so 2 minutes more left.
Maybe I'll just start. Okay. So
Okay.
So very good morning, everyone. And thank you again for coming to my class. So this will be our fourth lecture. And for the first half an hour of this course, I will talk a little bit on the membrane science and technology. Then after that, I will go for adsorption technology. Okay. So for this adsorption technology, I will consider this as quite a mature technology. Okay, but I'm going to deliver it in such a way that you know what is important, right, in the adsorption field. Okay, so before that, let's just cover back our membrane science and technology, so we can wrap up this topic. Okay, so this is a very long topic that we have been going through for the past 2 weeks. So we have covered introduction. We know what exactly is membrane, how it works, what are the driving force. For example, if you look at microfiltration, you have the pressure as a driving force. Right? Your reverse osmosis, you have also pressure. Then you have forward osmosis, you have the concentration gradient as your driving force. So different membrane, they work differently depending on the type of membrane and application. So they have different driving force, which means that if you want to have separation between different systems, you have to have different condition. Okay, so we have also looked at the type of membrane and their properties, okay, like UF, MF, and what can we do to classify them. Okay, they're classified based on their pore size and whether they are porous or non-porous. Okay. We also look at the membrane preparation with a particular emphasis on the phase inversion and interfacial polymerization technique. We also look at membrane components and characterization. So I already talked about characterization and how we can use SEM, EM, and so on to design our membrane, right? So today we want to extend a bit and look into the application of membrane in real life. Okay? A bit on the real life and what is needed, okay, for us to apply the membrane. So if you look at the membrane technology, is quite popular. Okay? Like yesterday, I attended this online conference. Right, quite a number of people talk about membrane. And then before this also, last year I attended some conference. They also talk about membrane and so on. So you can see that this field is really emerging. Okay? It's quite hot. Okay, so just want to continue from last week. So this is how we can design the RO plant. Okay, so in general, if you look at any RO plant, usually you have the feed source. Okay, feed source can be blackish water, it can be seawater. Okay, that one is the common one. So sometimes you also have secondary effluent as your feed source. Okay? And this feed source, okay, just to remind everyone, you need to pre-treat it. Okay, the reason for pre-treatment, very simple, is to remove everything that can damage the membrane. So your RO membrane that you have is very fragile, right? So when you have something like chlorine, right, added into the feed source, let's say your feed source has a lot of chlorine, or maybe it has a lot of particles, right? So when it goes to the RO membrane, it will destroy the membrane. Okay? You will have falling effect. Because as you know, most of the RO membrane, they are very thin. Okay, the selective layer is very thin, right? So if you have particles, these particles can somehow affect the thin layer. Okay, it can damage the that layer, so that you will have a lot of salt being pushed into the permeate side. Okay, so that's why we have to have pre-treatment. And pre-treatment, you can see that a lot of people are using different techniques depending on what system they have. So for example, some people use pH adjustment, some people use anti-scalant to prevent scaling. Okay? Some people use conventional technique like coagulation, ozonation, right? And so on. Okay? So after that, you have this membrane separation process whereby there are quite a number of parameters that you need to control. For example, the type module, this one we'll go through in a while. And then in terms of the recovery, how much water you want to recover from the system. You can calculate it. Okay, what's the concentration of the brine, okay, that you want to have, and so on. Because the brine concentration and the water recovery, they are directly linked to the energy that you need. Okay? More water you want to recover, that means more energy you need to put in. Okay? So after that, once you have separated the permeate and brine, the next step to do is to look into the permeate water quality, whether they are suitable for the purpose that you want to do. For example, if you want to use it for drinking water, right, you have to adjust the parameter so that it is suitable. For example, one example is that let's say you want to use this for drinking water, right? After RO treatment, your water will be very clean. There's no ion in it. So you have to add a little bit of ion so that you can adjust the water to be suitable for drinking purpose. Okay. Sometimes you also want to do some disinfection process. Okay? Not because RO cannot remove all the bacteria. It's because sometimes you want to do some chlorination so that you have post disinfection effect. Okay. That means the water is clean until it reaches the consumer. Okay. So on the other hand, the brine, okay, the brine itself is concentrated concentrated ions and all these rejects. Okay, so once we separate the water, of course, you expect that this brine will contain a lot of elements, right? If you are doing seawater desalination, okay, you can have heavy metals in the water, okay, like radon or maybe lithium, right? Sometimes you have other heavy metals. So you need to see this brine, you want to do what post-treatment so that you can have the most economical impact. Okay, because usually brine, some people prefer to recover the energy from the brine, right, through maybe pressure retarded osmosis process. Some people want to consider recovering the metals. Okay, as you know, we have lithium in the brine. We have maybe some other very precious heavy metal, although they are very low concentration, but they can be recovered. Okay, and the recovery of heavy metals, yeah, some people use adsorption process to selectively adsorb the heavy metals. Some people use many techniques, okay, ion exchange and so on. But in terms of whether it is practical to recover the metal from brine, it is another question. And I can see that there are several research, okay, looking into recovering metals today. So we don't know how this technology will progress. Okay. The membrane and the module, this is how it looks like. It's pretty big, right? You can see this one is like almost the size of a adult human. Okay, and it can have 8 elements. It can have 6 elements. Okay, usually it's in a spiral wound module. Okay, sometimes it can be a hollow fiber module. Depends on the application itself. Okay, so usually it's a composite polyamide. Okay, polyamide membrane. Because this one is easy to prepare and commercially available. Okay, and in terms of application, the condition that you need to do is it depends on what are the type of water that you have, brackish water or seawater. Right? Seawater, you have to have higher pressure, okay? And you have to have a more tolerance RO membrane compared to brackish water. Okay? So some information on the different types of membrane, commercially available membrane. So all these, they are the commercial name of the membrane. Okay, all these are the gray color one is the RO membrane, and the blue color one is the NF membrane. So you can see the difference in terms of the rejection. Okay, so rejection, this one we call it as rejection, NaCl rejection. So as expected, nanofiltration is not as good as the RO membrane in terms of rejecting the salt. Okay, but of course, there's a cost for rejection, high rejection of NaCl. If you have high rejection of NaCl, you probably have a lower pure water permeability. Okay, you can see here, right? Okay, so when you purchase a membrane, usually you will get this kind of a brochure. This brochure, this information will tell you about a lot of things. Okay, so you can know what is the sodium chloride solution concentration, the one that it tests, and then what is the permeate recovery, and then pH range, and so on. All these data, they are available and provided by the manufacturer. Okay, so this one is also the same. So this one I will not talk a lot on this. You can go through it. And this one, the chlorine tolerance is important. Okay, and when you want to apply a particular membrane, of course, you need to check the operational temperature. So usually the polymer membrane or organic membrane, they cannot tolerate a high temperature. Okay, for this case, polyamide, you can only go up to, I think it's 45 degrees Celsius. Right? So for ceramic membrane, you can go higher. It can go up to 100 degrees Celsius or maybe higher, okay, depending on application. Of course, you know that water boils at 100, right? So that means we usually apply ceramic membrane for other application. Okay. Okay, so for membrane pressure vessel, this one is what we call as a pressure vessel. Okay, this whole thing, and inside this pressure vessel, you can see there are a lot of these things. Okay, this box here. Each of these is a membrane element. So you usually have 6 to 8 elements inside the pressure vessel. Okay, and usually we represent it as this way. Okay, the feed comes in, and then this is the how we draw the each of these pressure vessel. Okay, so some additional information for you to have a look to know. We can calculate a lot of different parameters using all these equation. For example, mass balance, recovery, and rejection. Okay, and for real application, if you go to the RO plan, usually they will look into applying based on the cross-flow filtration configuration. Okay, so this way. I hope that you still remember this configuration. We talked about it last week. So this is usually used for UF, NF, and RO membrane. Okay, so very seldom you'll see people use the dead end configuration, okay, because of the fouling factor. Okay. So if we look at the data, the recovery data, right? By right, if you want to recover more water, you will need to use more energy because you are actually pushing the water against the osmotic pressure. And for seawater, osmotic pressure is very, very significant. Okay? It's very, very high. That's why sometimes it's more economical to recover only part of the water, maybe up to 50%. Okay. For I have this new water recovery. Okay. This new water is secondary effluent water. Okay, so the secondary effluent from wastewater treatment plant. Okay, after the secondary treatment, it is channeled to the RO system, and then this RO system allows recovery of the secondary effluent. So new water is a trademark name for secondary effluent reclaimed water in Singapore. Okay, so if you go to this, if you go to Singapore and you mention new water, most of the people in Singapore know what exactly is new water. Okay, so the advantage of having a high recovery is that you probably have lower feed flow rate for a given permit, and the other one is smaller volume of concentrate generated, which means that the brine that you have, the waste that you have will be a lot smaller. Okay, compared to when you have lower water recovery. So when we talk about recovery, okay, recovery means that how much water, what is the percentage of water that you can take out from the waste, okay, the wastewater. Let's say seawater, you have seawater and you can recover, you can take out 50% of water from it. That means your recovery is 50%. Okay. But disadvantage, of course, if you are using high recovery mode, you tend to have fouling. Okay, probably have higher osmotic pressure and lower permeate water quality. So usually when you have this higher recovery, that means on the other side you have very high osmotic pressure. So some of the contaminant from the waste, okay, on the concentrate side, may leach into your permeate water. That's why you have lower permeate water quality. Okay, so today we want to try to see whether we can achieve this zero liquid discharge to an extent where we can recover 100% of water. Okay, there are of course advantages of doing so. Okay, because it will give you more water. You don't have to worry about the water problem, right? It will cause less environmental problem, as you know, because the waste that you generate from recovering water will be lower. Okay, because if you can recover 100% of water, those wastes will probably become solid. You know, if you have a seawater, right? If you remove all the water from the seawater, you will have all those solid remain in your container. Okay, so that one is the salt and the dissolved solids, right? And another one is that you will probably have increased regulatory pressure on brine disposal. Okay, but of course there are also penalties like lower water quality, higher osmotic pressure, and so on. Okay, so this one you can see here, this figure, right? This is in Sydney. Okay. Sydney, they are doing this kind of treatment. Okay, they are also trying to recover the secondary effluent, right? So in general, if you look at the treatment of water, right? If you using RO technology, you want to use zero liquid discharge method, right? Which means you want to recover all the water up to 100%. Seawater is practically almost impossible to do so because of the high energy demand. Right? Blackish water still okay, but also very difficult to achieve 100%. So the wastewater that is the most likely one to achieve 100% is the secondary effluent, right? So a lot of different countries, they are working into using RO membrane to recover and reuse their water. And sometimes the government will provide incentive, okay, for the industry to reuse their own water. Okay, so it depends on country. Different country, they have different regulation and policies. So this is just to show you that this is how a fire looks like. I believe you have been exposed to this before. Keep coming in, and then after that, permeate will come out from this side. Okay. This one, they are just wrapping it in the spiral method. Okay, it's actually like a flat sheet membrane. Okay. So this one is more on to tell you how we can calculate different parameters. Okay. Okay, so in each of these pressure vessel, right, you have various membrane element, right? So each element you will use it, okay? And once let's look at this element, right? Once you have this water going in, right? Let's say your feed is about 75, okay, gallon per minute, right? The flow rate. It goes inside, and then after that, most of the water will just come out from each of these element. Okay, towards the end, the feed, okay, will only be like 13, right? This part will become like concentrate. It will be like 13 gallon per minute, and you can recover about 36 gallon per this amount of water. Okay, so there are many ways, many configurations that we can do. Okay, usually people, when you want to design and implement this RO system, they can design it in the way that whether they want to have high permeate recovery, okay, high water recovery, or they want to have lowest energy configuration, or they want to have the lowest falling configuration. So all these depends on the the desire of the manufacturer, the desire of the operator. Okay, the operator themselves will be the one who decide whether they want to have more water or whether they want to reduce fouling. So in the end, the most important thing for this kind of application is the cost itself. So the cost of operating and getting water from the membrane unit have to be as low as possible. Okay? But sometimes you have pressure from the government or maybe from the people because they don't have water in their house. Okay? They will give you pressure, and you have to increase the permeate production. So this is very common problem. And when you increase the permeate production, of course, you will increase the falling rate. But then there are pros and cons. That's why we have to find a balance between all these. Okay. So in terms of arrangement, let's look at some arrangement. This arrangement have the pros and cons. For example, if you look at the staging, okay, you need four different pressure vessel. This one, 2, 3, 4, right? 4 pressure vessel. And in terms of the water recovery, right? In terms of recovery, let's say you have 80 in the feed. Okay, 80. The flow rate is 80, right? And then it goes to each of these membrane. Okay, the first one and the second one. Of course, you split to 40-40, and then after that you go to another one. It becomes 20 because you recovered 20, right? And then in the end, you will get 60 water, okay, your permeate, and 20 your concentrate. Okay, so this one for this recovery, you need 4 different pressure vessels, right? And the other one, okay, the tapering mode, whereby you only need 3, but you can achieve the same effect. You can see from here that this kind of configuration actually plays a very important role in terms of whether you can achieve the highest recovery at the lowest cost or not, right? So some people may wonder why we need to have 4, right? These four different pressure vessels, and you only achieve what a 3 can achieve, right? So reason sometimes people tend to choose the 4 pressure vessel instead of 3. Sometimes it's because of the falling issues. Okay, but sometimes it's not practical to use the staging also because it depends on the condition. Okay, so we have another one is the multi-stage array. Okay? You can look at it. I don't want to cover all this too much because all this is in terms of the design. Okay, so multi-stage design and multi-pass design. Why we choose all this? What you need to know is why we choose all these different configuration is because of different reasons. Sometimes we want more permeate, sometimes we want more less falling, right? So it depends on the operator. Okay? They can choose whichever configuration they want. Now we have a system whereby we just need to press a button and the configuration can change, right? Very easily. So it's interchangeably. Okay. Okay, this one we have also the train setup, okay, recycle loop, and so on. So all these configuration they have their own purpose. So to control the operation, people use software. Okay. Now it's very simple. Only software. You just need to press certain command in the software, and all those all those design can be implemented. Okay. So if we compare different stages, like I said, different stages will be dependent on the operator themselves. One stage, maybe if you want to do one stage, you can recover maybe 53% of water. Compared to 3 stages, maybe you can recover more, 55%, right? But of course, if you look at the cost itself, 3 stage is relatively cheaper, right, compared to the 1 stage, right? Why 3 stage is cheaper than 1 stage? It's because the brine that you have in 3 stage may be containing a lot of energy. right? So the brine in the 3-stage can be used to provide more energy compared to the brine in the 1-stage. Okay, sometimes they do recover the energy from the brine, and there are also a lot of reasons why 3 stages sometimes can be cheaper than 1 stage. Okay, but of course, this one is just the operating cost. It does not include the capital cost. So capital cost for 3-stage is obviously higher compared to the 1-stage system, because you need to have a bigger space. You need to install more RO membrane and so on. Okay, so got pros and cons lah. And yeah, I don't want to talk more on this because I already covered this. In terms of pre-treatment, you can go through this. What type of pre-treatment that you have, right? And what are they for? Okay. Okay, so this one in terms of post-treatment and brine post-treatment. Also, you can see we have quite a number of post-treatment technique, okay, depending on the type of contaminant that you have after your part of treatment. Okay. Okay, so pilot scale design, yeah, we can see that there are quite a number of pilot scale. Okay, this is one of the pilot scale. I believe this is in Europe. Okay, and they recover 75% of water to this 2-to-1 multi-stage array. Okay, that means they have two become one. Okay, and it's in a multi-stage setup configuration. Okay, and it's interesting to see that for this system, they control it and optimize it in a way that after 58 days of operation, there's no fouling issues, okay? Which means that this particular system is quite sustainable. Right? You can use it for a long run. Okay. So another one example that I want to share with you, maybe some of you may have heard of this new water before. Like just now, I mentioned a bit on new water, right? So I just want to share a bit on this technology. So I believe this is one of the very groundbreaking technology. Okay, because if you go to any conference, right, any conference in the world, if you have the opportunity to go, definitely when people talk about water reclamation, some people will just to some extent mention Singapore word. Okay, some of the presenter will use Singapore. Why is that? Because of new water. Okay, so in Singapore, I believe they are one of the first country to produce water from secondary effluent. Because you know that Singapore is a very small country, right? So a small country with very limited water resources. Okay? So because of this, they are actively looking into getting water from everywhere. Okay. So currently, if you are aware, Singapore have 4 water sources. Okay? One is from Malaysia, right? One is from seawater, which means desalination. One is from stormwater, right? The other one, if not mistaken, is from this reclaimed water. Okay, so reclaimed water is water that they reclaim from secondary treated effluent. Okay, so let's say you go to the bathroom toilet, right? So you secrete all those liquid into the bathroom, and it goes to the wastewater treatment plant. So this wastewater treatment plant, usually it undergoes primary treatment, which means we remove all the solids, right? And then after that, it goes to the secondary treatment. So secondary treatment is biological treatment. So the effluent from the secondary treatment will be used, and it will go to the microfiltration, okay? And then after that, it goes to the reverse osmosis. And after reverse osmosis, the water is very clean. You can drink it directly. But to provide an additional barrier, right, protective barrier, they also use the ultraviolet disinfection. Okay, so through this process, you can get a water that is very pure, okay? Pure and it's drinkable. So if you have a chance to go to visit the new water plant, So they will give you a mineral water, right? They will give you like a mineral water bottle, right? And then once you drink it, then they will tell you it's new water. So it's like you're drinking toilet water, right? So but it's clean, okay? So this is already been polished, right? It's very clean. So it's very safe to drink, okay? But of course, some what I know is that some professor in Singapore argue that new water is not as clean as what people claim to be, because it could contain something. So this is for another topic, okay, that we will discuss later. So we have quite a number of different contaminant being removed. As I said, the first step is microfiltration. So it removes a lot of these large particles, bacteria, and so on. Okay. So after that, it goes to reverse osmosis, whereby all these inorganics, virus, everything is removed. Okay. So direct reverse osmosis is very clean, but additional barrier just in case some bacteria escape. Okay. It get into the permeate. So they have UV disinfection. So in terms of water quality, you can see it for yourself. If you compare with the WHO standard or tap water or maybe reservoir water, okay, the difference between new water and other water is quite significant. Okay, new water is very, very clean. Okay. This shows that the RO technology is a very promising technology to obtain very clean water, okay, from contaminated water. Okay. So before you design any RO membrane, usually you have something called the design parameters. Right? All these, they are the design parameters. And once you design it, then you test it. The actual parameters for this new water demonstration plant is significantly better than the design parameters. Okay? The intended numbers. Okay, you can see from here this UV disinfection expected is 4 log removal, which means 99.99%. But the actual one that has been achieved is 99.99999%. So it is quite significant. Okay, okay, that's all for my membrane topic. Okay, I hope you get something from the membrane topic. It's quite a heavy topic, I would say. So if you have any queries on the membrane topic, I am more than happy to, yeah, I can see, yeah, someone asked a question. Mineralization is post-treatment. Okay, how to add the mineral level in this case from salt solution? Yes. Okay, so after RO treatment, right, your water is like deionized water. So to add in, they have to look at the quality, water quality, drinking water quality, the standard and so on. So yes, they add in, for example, usually they add in calcium or magnesium into the solution. So calcium, yeah, calcium salt, okay, they add in calcium salt to the solution. They will not add something that contains, what you call that? Organic elements. Okay. Yes, they adding calcium. Not mistaken, it's calcium carbonate. Sometimes they add in that. But definitely it's a salt. Okay. Okay. So any questions that the students want to ask? If not, then we will look into today's topic. I believe today's topic will be more interesting. I will mix a bit on how to innovate in adsorption technology with the application of adsorption technology. Okay, so what we are going to look into today is number one will be fundamental and application. So I want to introduce a bit on what exactly is adsorption. Okay, and I believe most of the students probably will have some exposure to adsorption already. So I will not go into too details on what adsorption is and all these isotherms and so on. But what I'm going to do is I'm going to share with you some very interesting things that maybe you are interested in. Look into what are the problems that we have today in terms of the fundamental application, okay, so that you can start your thinking to see is these results applicable or not. Okay, let's say you go to the journal, right? You read a journal, they publish a paper on adsorption, okay, and you want to know whether these results are they reliable or not. What should I question from the results? This is what I'm going to share with you. Okay. And then after that, I'm going to cover these 3 topics. Okay. These 3 will be more on how we can innovate adsorbent. Okay. What are the key things that people look into when you want to publish a high impact factor paper in adsorption area? Okay. So I'm quite familiar with adsorption. I personally have worked on adsorption for many years. Okay. In fact, I have published several papers in adsorption technology. So I roughly know what are the editors and people looking for when you want to have an article in adsorption field. I will share with you in a while. Okay, so let's look into some fundamentals of adsorption. So I'll start off with telling you what exactly is adsorption. Okay, so adsorption in general is just a process whereby you are concentrating the pollutant on a surface. Okay, so I'm going to tell you in water and wastewater treatment area, okay, how we look at this adsorption process. Okay, in general, it's just a process whereby you have the pollutant, and the pollutant is attached to the surface of your adsorbent. Okay, so adsorbent is defined as something that has a very unique surface, whereby you have the adsorbate. Okay, adsorbate is the things that you have this one, okay, that can attach on the surface of the adsorbent. Okay, so we have adsorbent and adsorbate. Okay, some nomenclature for you to know. Okay, so usually adsorption happens because of the surface energy. Okay, which means if your surface have a certain functional group, or maybe your surface have deficiency in terms of the energy, okay, or maybe your surface have high energy, right? Your pollutant can be able to adsorb on the surface or attach to the surface of the adsorbent to minimize the overall energy. Okay, so your adsorption process can happen between liquid and gas, liquid solid, or liquid and liquid. Okay. So there are confusion between adsorption and absorption. Okay, so there are very significant difference, okay, between adsorption AD and absorption AB. Okay, these 2 processes they are very different. Okay, in fact, I have known PhD students who are confused, okay, between adsorption and absorption. Even if you type in Microsoft Word, right? This Microsoft Word is also confused, right? It will autocorrect adsorption to become absorption. So you have to be aware of that. Okay. So in general, adsorption, AD, means a pollutant attached to the surface of the adsorbent. Absorption means that the pollutant move inside into the back of the face. Okay, there's a difference. So what we are going to talk about is this one, the one with the AD, adsorption. Okay, so yeah, this is the definition, the exact definition of adsorption and absorption. Okay, and some example, okay, of absorption is like a sponge. Okay, you have sponge, right? So if you take this sponge, you put inside the water, then the sponge will be able to absorb the water. Okay, this is an example of absorption. Okay, so in terms of adsorbent, we have a number of adsorbent. Okay, for example, you have silica gel, you have activated alumina, okay, and so on. All these adsorbent, they have different use case. Okay, for example, silica gel, usually people use it for removing water, right? So if you go to the supermarket or somewhere, you buy a pack of maybe biscuit, right? Inside the biscuit, sometimes they will put a pack of silica gel, right? So this is to absorb the moisture. Okay, so this adsorption of moisture is reversible. So you take the silica gel, you put it in an oven. So all this moisture will go away, and then you can reuse the silica gel again. Okay. So other types of adsorbent like activated alumina, activated carbon, polymer, clay, and even zeolite, they are quite widely used for various applications. Okay? But for water and wastewater treatment, the most widely applied adsorbent is the activated carbon. Okay? So activated carbon, they are very popular, okay, for water treatment. Okay? You seldom will see people want to use zeolite, alumina, or silica gel for water treatment. Okay? One of the reasons why activated carbon is popular is because it is cheap. Yeah? It's very cheap compared to others. Okay? And it is also, there's no risk of contamination. Okay? If you use zeolite, let's say you use zeolite and your zeolite contains, let's say, heavy metals. So this heavy metal sometimes can leach into the water. Okay, and activated carbon itself, we will not have so much of the problem. Okay, so this one I already talked about adsorbate and adsorbent. Okay, what's the difference between adsorbate and adsorbent? Okay, this is how we name it. Okay, so why activated carbon is so good? Is because it has high surface area. Okay, so activated carbon itself is very porous. Okay, and because of the porosity, it has a very huge amount of surface area which can be used for adsorption. Okay, so in adsorption process, you always want to get something that has high surface area, because the higher surface area you have, the better adsorption capacity you will get. Okay. As I said, driving force of adsorption is because of the energy on the surface. Okay. And the common adsorbent, as I mentioned, is the activated carbon, which can come in two different forms. One is the granular form. The other one is the powdered form. So the difference between granular and powdered is in terms of the size, okay? The size of the activated carbon. So granular is relatively larger, right? Whereas powdered is, when you know powdered, right? It's very, very small, okay? And the characteristics of GAC and PAC is also very different. Okay? GAC, usually you will have a lot of macropores, mesopores, and micropores. Okay? Whereas in general, powdered activated carbon have abundant micropores. Okay? Very little amount of mesopores and macropores. Okay? So I hope you are familiar with the term mesopores, macropores, and micropores. Okay? In general, macropores are the largest pore, followed by mesopores, and the smallest one is the micropores. Okay. So in terms of kinetics of adsorption, of course, GAC adsorption will be slower compared to PAC. Okay. But GAC has its own use case. So GAC, because it's larger, it's relatively easier to pack into a column. Okay? Whereby PAC, you cannot use it for column study. Okay? Column means that continuous adsorption process. Okay. You can only use a batch for PAC system. Okay. So for activated carbon, it has to be porous. That's why we apply it. Porosity means high surface area. And to prepare activated carbon, usually we use organic matter, and then we carry out pyrolysis process in the absence of air, so that you can end up getting a black color carbon material. Okay, and generally activated carbon has the following properties: positive charge, porous, and large specific surface area. Okay. So how it works? Generally, you just have to take this carbon, you put it in the water, you throw it inside water that contains contaminant, and then all those unwanted substance, organic pollutant, they will be attached to the carbon. Okay? So once they attach to the carbon, we consider it as removal. They are removed from the water. So the pollutant itself, okay, the chemical, it can attach to the carbon by two different means. One is through chemical attraction, the other one is physical attraction. Okay, so for this one, what are the difference? It's in terms of the adsorption energy. Okay, so for physical adsorption, the energy required is low, okay, relatively lower, and you are actually forming something called a van der Waals interaction. Okay, which means that the pollutant is absorbed quickly on the surface of the activated carbon. This process is reversible. Okay, and this process can also lead to the formation of monolayer, double layer, and more than 2 layers, 3 layers, and 4 layers. Okay. And what is important for physical adsorption to happen is the surface itself, because the pollutant attached to the surface directly, which is why the higher the surface area that you have, the more likely physical adsorption will happen. Okay, so these are the interactions of a physical adsorption. We have dispersion forces, ion dipole, ion-induced dipole, and so on. Okay, so many different types of interactions. Okay, depending on the functional groups that you have on the surface of your adsorbent. Whereas if you look at chemisorption, chemisorption means that you are forming chemical bond on the surface of the adsorbent. Okay, so if you have this kind of formation of chemical bond, then your adsorption process may not be reversible. Okay, so this one usually it requires high heat of adsorption, okay, to form a very stable bond, okay, which can be covalent. Covalent, you know, is a very strong bond, right? So in terms of whether it's reversible, it's not really reversible. Okay, and what is important for chemisorption to happen is the functional group, okay, the active sites, okay? The active sites that can cause bonding, okay? And it's not the surface area, which means that if you have activated carbon that only have very limited active sites, right, then you will not have a very high adsorption capacity. So activated carbon to work, you have to have several things. One is you have to have high surface area, and activated carbon relies on physical adsorption. So the carbon that you use for water and wastewater treatment, mostly we want physical adsorption to happen. Okay, because physical adsorption, if you compare with chemisorption, right? Physical adsorption is able to attract more different pollutant, okay, different types of pollutant. Okay, it's more versatile, right? And what you are doing is that you are actually attracting that particular pollutant onto the surface so that you can actively removing it. Okay. So what happens in terms of mechanism is we have 3 steps. The pollutant has to come into contact with the activated carbon. It goes into the pores, and then it is adsorbed. So you can go through this. Okay, so general application. In terms of substance that activated carbon can remove, right? It is not so good when you want to remove things like arsenic or bacteria or virus, okay? Because bacteria or virus, it cannot be adsorbed, one thing. And sometimes bacteria, they are too large, right? They can block the pores of your activated carbon. Okay? AC can be used to remove bad taste, chlorine, and radon, okay? And VOCs, volatile organic carbon. Okay? But not so good when you want to remove things like nitrate, iron, and so on. Okay? Especially heavy metals. If you look at the larger scale application, okay, in the wastewater treatment plant, generally AC, they are not used to remove heavy metals because of their low adsorption capacity. Okay. Of course, if you look at the literature, you can see a lot of people reporting the use of activated carbon for removing heavy metals. But that one, they design it, okay, to remove the heavy metal. Okay, they design the activated carbon for that application. But in general, when you look at the real application, it has poor heavy metal removal. Okay, so okay, that one is more on the very general introduction of activated carbon. So do you all have any questions related to? Yeah, okay, I can see one question. If we use zeolite adsorbent, what kind of zeolite do we use? So we have quite a number of different types of zeolite. Okay, depending on what type of pollutant you want to remove. Like ZSM5, that one is one of the most common one, right? And then you also let me see what else. That's the one that I know, like ZSM5 that people use. Okay. Besides that, other than that, I'm not very familiar with what kind of zeolite people use for water treatment, because generally people don't really use zeolite for large scale water and wastewater treatment. Okay, you won't find it everywhere. Okay? Most of the time, people use activated carbon. So a very simple reason is because it is more effective compared to zeolite. Zeolite is more selective, and if you have water contaminated with, let's say, heavy metals, it is often also mixed with organics and so on. So if you want to use zeolite to really purify the water, it's not as efficient as the carbon. But I know that there are some industries that use zeolite, okay, I have another question. Oh, before that, I know that some industry they use zeolite to recover their metals. Okay, some people do that. Okay, some people use zeolite to recover certain metals from their wastewater. Okay, and most of the time zeolite they use it as a catalyst. Okay, if you look at the application of zeolite, is really wide. So one of my colleagues, I think Dr. Fitri, is working very closely with him. He is very interested in working in zeolite. He developed a lot of zeolite for catalysis, okay? But not for water treatment, because as you know, there are better things to apply zeolite in, okay, compared to water treatment. Okay. So the next one is I have made activated carbon, but the surface area is still low. Okay, how do I increase the surface area? So this one, I'll talk about this in a while. So I think you have to activate it. Okay, so your activated carbon have low surface area, probably because you have not activated. Okay, so I'll talk a bit on this one. And yeah, another one question is in terms of adsorption mechanism. Okay? is there any difference between granular activated carbon and powder activated carbon? Okay. Okay, so AC, powdered form and granule form, the surface functional groups, they are the same. Difference is in terms of the size. Okay, so if you talk about interaction between pollutant and the adsorbent, both are the same interaction. But in terms of the mechanism, adsorption mechanism, like just now what I showed you, this mechanism. Okay. Generally, if you look at the granular activated carbon, right, the pollutant will go here first. Okay, it will be on the surface, and then it will diffuse into the macropores, then mesopores, and then finally into the micropores. Right. So in terms of the ability of the pollutant to reach up to the micropores, it could take longer compared to the powdered form. Okay, because you have mass transfer resistance, and because you have a longer pathway, longer length, you have to go from macropores to mesopores to micropores. That's why you will see that the time taken for granular activated carbon to adsorb the pollutant, the contact time will be longer compared to the powder activated carbon. Okay. The powder activated carbon, most of the pores, they are micropores. Okay, so micropores, they also in general follow the same mechanism as what I have presented here, 1, 2, and 3. Okay, just that it's faster because it can reach the micropore relatively fast. You put it inside the solution, all the pollutants can be in contact, and then all this pollutant will just go into the pores. Okay? It will attach to the pores. Okay? This is generally what happens when you have adsorption process. Okay, just that the difference between granular activated carbon and powder activated carbon is the pore itself. Okay, if we have bigger pores, that leads to a smaller pores, which leads to a even smaller pores. Then to travel from the bigger pores to the smaller pores, it takes more time. Okay, so that's what I can say in terms of the mechanism. In terms of the surface area, surface functional groups, they are all the same. Okay? What GAC have, EAC also have. Okay, so there's no difference in terms of the interactions. Okay, so let's talk a bit on adsorption, isotherm, and thermodynamics and kinetics. Okay, so I assume that you all have been exposed to these 3 things. Okay. So I'm going to discuss it in a more in-depth. Okay, I'm going to discuss it more in depth. Okay, so why we want to have adsorption isotherm? Right. So if you Google any adsorption paper, so almost 99.9% of adsorption paper will have adsorption isotherm. Okay, they will study the adsorption isotherm. Okay. And the reason why we want to have adsorption isotherm is because we want to look at the behavior of adsorption, okay, under equilibrium condition. So by studying the behavior, we can know what is the adsorption tendency, which means is it faster or is it slower, okay, towards a certain pollutant. We can also know about the capacity. That's why we need to know every time when we design a new adsorbent, how we can use this isotherm. Okay, how this adsorbent behave. Okay, example of an isotherm. Okay, this is an example. Okay, it's actually a plot of adsorption capacity, equilibrium adsorption capacity. Okay, this is QE represented by QE against CE. Okay, this is the equilibrium concentration. Okay. So you can see that there are a lot of points here. Okay, so basically what people do is, let's say you have a fixed amount of adsorbent. Okay? Your adsorbent is 1 gram. Let's say you fix it 1 gram per liter. Right? Then you carry out the adsorption process. Let's say you add in 100 ppm, okay, of the pollutant into the system. Okay, that means your system of 100 ppm of pollutant, you have 1 gram per liter of your adsorbent. So this adsorbent will absorb the pollutant, right? So at equilibrium, equilibrium means that that rate of adsorption and rate of desorption, they are the same, right? So at equilibrium condition, maybe at equilibrium you have about 80 ppm of pollutant being adsorbed. Okay, so once you know 80 ppm of your pollutant is adsorbed, you can calculate what is your QE. Because QE is generally defined as milligram of pollutant adsorbed per gram of your activated carbon. Okay, so let's say you have 1 gram per liter activated carbon, you have 80 milligram per liter being adsorbed, right? 80 divided by 1 gram per liter, okay, is your QE. So the concentration remaining in the solution is 20 ppm. That one is your CE. Okay, so from here you can see, let's say you have 20 and your adsorption capacity is 80, right? 80 is around here. That's your point. Okay, this is how you understand the adsorption isotope. Okay, so each point of this one correspond to different concentration of pollutant at a fixed adsorbent dosage. Okay, so this is how usually people do to get the adsorption isotope. So if you look at the literature, right, you will see that once people study this adsorption process, okay, and they obtain this data, they will tend to fit it with the Langmuir and Friedrich equation. Okay? These two are the most fundamental equation. Okay, okay, so before I proceed, I have a question on how to determine the equilibrium concentration for CE. Okay, so CE is very simple to determine. Okay, so let me just say it again. Let's say you have a solution, right? This one is your, let's say 100 mg per liter. Okay. You have a solution containing 100 milligram per liter of pollutant, right? You add in PAC. Let's say your PAC is 1 gram per liter, right? And then after equilibrium, right, your solution concentration becomes 20 milligram per liter of your pollutant. Okay, so this 20 is your CE. So 20 milligram per liter is your equilibrium concentration. Okay. So how you know whether equilibrium has been achieved, right? Some people may want to ask how you know, right? So you have to conduct the study at different time. Okay, so first study when you want to do adsorption process is always to check the contact time, which means the time taken for equilibrium to happen. Okay, so you have to do this. You have to get the time versus concentration data. Okay, concentration of pollutant data. And what we will see is that you will have initial rapid adsorption, okay, followed by flat line. Okay, so this flat line, okay, is the time where your system has already achieved equilibrium. So you can take this time as your equilibrium time or your contact time. You can take this time as contact time, right? Because you can see that it has already flattened, okay? Which means the rate of adsorption and rate of desorption, they are the same,
right? That's why we want to get this as a contact type. You cannot take this point, okay? You cannot take this point because this point adsorption is still happening. Equilibrium has not been established yet. So you can only take this point onwards, okay? From here to here. Okay, so once you get a contact time, next step is to study the adsorption equilibrium. Okay? You vary the concentration of your pollutant. So let's say this one we do it at 100, then we do it at 200, then we do it at 300, right? And then your equilibrium concentration will change. Okay? At 100, maybe you have 20 milligram per liter. At 200, your equilibrium concentration may be at 100. Right? At 300, maybe your equilibrium concentration becomes 200. Okay? So after getting the data, you can plot out this graph. Okay? You have the equilibrium concentration, and you calculate what is the amount adsorbed. Then you can plot the isotope. Okay? So a lot of people use something called the Langmuir equation and Friedrich equation to model how adsorption isotope happens. Right? So generally, if you look at Langmuir, Langmuir is about equilibrium adsorption derived using kinetics, right? So in general, your adsorption process, you can actually use it and represent it using this kind of chemical equation. You have your solute or your pollutant, you plus with your adsorbent, right? And then you will get this one, SA, which means your pollutant has been adsorbed on the activated carbon. Okay, so usually we can say like that. The initial concentration is CO, right? And then after equilibrium, the concentration of your pollutant becomes CE. But this SA, okay, adsorbed species will have a value, right? Initially it's 0, then it becomes C0 minus CE. So we usually prefer to present it, okay, in a different way. Okay? We prefer to look into this kind of adsorption system in terms of the surface coverage. Okay? That will be more meaningful so that we can actually use this surface coverage to measure the adsorption capacity and also to look at the lifespan of the adsorbent if we introduce it into the system. Okay? Which is why in adsorption study, usually we prefer to present it like this. Okay? Initially, you have C0. At the initial state, your surface coverage is equals to 0. Okay? Surface coverage means that how much surface has already been taken up or occupied by the pollutant. Okay? If it's 0, then that means your surface is still not contaminated. Okay? It has no pollutant on the surface. Okay? So if it's at equilibrium condition, you have this value, which means that this is a theta, right? Theta equilibrium, which means that you have certain pollutant being adsorbed. Okay? It can be used to reflect the number of adsorption sites. Okay. Okay, so I'm not going to give you a very detailed derivation of Langmuir. Okay, but if you look at the Langmuir model, it is derived based on this one. Okay, the kinetics. Okay, it's derived based on the rate of adsorption is equals to the rate of desorption. Right. So from the rate of adsorption and rate of desorption being equal, you can actually derive the Langmuir isotope equation. Right. This one you can go to Wikipedia. Wikipedia provides a very good explanation on how Langmuir model is derived. Okay, so I don't want to go too mathematical, but what you need to know is that this is the product of your Langmuir adsorption equation. Okay, this is the solution, right? This equation, it has certain meaning. So once you derive the Langmuir equation, you will see that you will get two parameters. One is the K value. Okay? This one is the Langmuir constant. Okay? This K value is the equilibrium constant of adsorption. Okay? When you do the derivation, you will find out that this K value is also the same as the equilibrium constant, okay? Which means K adsorb over K desorb. Okay? And you have another one parameters in the Langmuir model. Probably you have seen this when you read the adsorption paper, Umax. This is the Langmuir maximum adsorption capacity. Okay? So remember, Langmuir, you have two very important parameters. One is the Langmuir maximum adsorption capacity. The other one is the Langmuir constant, okay? Or also known as equilibrium constant of adsorption. So these two values, right, these two constants, it has a significant meaning. Okay? So this is this slide is just to show you how to calculate the adsorption capacity. Okay, you can go through this. Okay, so what I want to share with you is in terms of the parameters. Okay, so when you want to conduct a study and you will get the Langmuir model, you will get two parameters. So the first parameters, the equilibrium constant, it reflects the adsorption tendency. The higher number you have, the higher value you have, the better tendency for that particular pollutant to be adsorbed. So you can see from the graph here, right? Your KEQ, okay, your K value is smaller. This K value is larger. So you can see that larger KEQ means that you have greater tendency. It achieves better adsorption, okay, at a faster rate. So, okay, so in general, this parameter, the K parameter, logically, if you look at it, is the equilibrium constant, right? So equilibrium constant, the larger you have, that means the rate of forward reaction is faster, right? Because your K is always equals to K, okay, K over K prime, okay, whereby one is the forward reaction, one is the backward reaction, right? So when you look at the K value, if it's larger, that means your tendency will be faster. The other one is the Qmax. Okay, Qmax is the parameter that reflects the adsorption capacity. So, but this is only theoretical, okay, which means that it does not really reflect the actual adsorption capacity of the adsorbent. It is only theoretically derived maximum adsorption capacity. Okay, but most of the time, from my experience, it does give quite a good estimate, okay, of the adsorbent. Okay, but of course, you know the limitation of Langmuir model. Okay, if you studied Langmuir model before in the previous course, you know that if you want to apply Langmuir model, you have three conditions that has to be met. Okay, three assumptions. One is that you have no lateral interaction between the pollutant on the surface. The other one is that monolayer formation. And the other one is that energy of adsorption is equal in every site. So these are the three assumptions of Langmuir model. And in most cases, all these assumptions is not so valid because you know activated carbon, when you have adsorption, you have more than one active site. This means that the adsorption energy may not be equal throughout the activated carbon. The next one is in terms of formation of monolayer, right? Monolayer formation is really not really significant, okay? In this activated carbon, usually you have more than one layer formation. Okay, it's not just a monolayer adsorption process. What I mean by monolayer is that, let's say you have adsorbent. The first layer, we call it as the monolayer. Okay, and Langmuir model only assume that monolayer is formed. But if you look at the actual adsorption process, you may have more than one layer. Okay? You can have adsorption on the second layer, third layer, and so on. Okay, so because of all these things, when you want to use this Langmuir model to estimate the Qmax, okay, it could be problematic. And of course, sometimes it gives a good estimate. Okay. So I want to bring a question to you all. Okay, if you look at the Langmuir model itself, right? If you look at what people have used up to today, a lot of people are using Langmuir model. This K value here, K value, does it has a unit? Yes, right? It has a unit, right? The K value has a unit of usually liter per mole or liter per milligram, okay, depending on the unit of measurement that you use. Okay? But the next question that I want to ask you all is that, do you think equilibrium constant have unit? Okay? When you study equilibrium constant in your analytical chemistry, right? Often we don't have unit, right? Let's say water, H2O, right? Dissociate to give you H plus OH minus. Okay. So if you want to write an equilibrium constant, K is equals to H plus OH over H2O. Okay. So when you want to write the equilibrium constant, right, so you will see that this equilibrium constant have no unit, right? But when you want to talk about Langmuir K value, which is also the equilibrium constant, this equilibrium constant, it has a unit. So why is that like that? Okay, why there's a discrepancy in terms of the unit in equilibrium constant? So this kind of question you all have to ask, okay, when you are reading journals. Okay, so there's a fundamental reason for this. But I'm not going to tell you what's the fundamental reason, but I hope that you will be able to do the research, okay, to find out why this Langmuir equilibrium constant has unit, but the usual equilibrium constant that we do does not have any unit. Okay, so this is something like a homework for you all to think of. Okay. So once you get the data, you will want to plot using Langmuir model, right? So the data that you have to have is the QE against your CE, right? Your adsorption equilibrium and the equilibrium concentration. So how you can determine your K and Qmax? Okay? Usually we have several ways, okay, using the Langmuir model. Number one is using non-linear regression method, which means we directly take this Langmuir model, we feed it, okay, feed it to the equation. Okay? Then you will end up getting a curve, something like this, right? This is how the Langmuir model, Langmuir non-linear form looks like. Okay? Then from here you can use the certain parameters. You can adjust certain parameters in MATLAB. Usually you need to use MATLAB, a software to do this kind of non-linear regression, because I don't think you can do it in Excel. Okay, so if you use a MATLAB, you adjust a few parameters, and you will get your Qmax and K value. Okay, some people want to avoid using non-linear, maybe because they don't have MATLAB or they don't have experience doing non-linear regression, so they convert it into linear form. Okay, you can have the B, this B form, Lineweaver-Burk form. Okay? This is one of the linear form. Okay? So you can convert this into a linear form. Okay? So this is your y equals to your slope. This is your x plus your y-intercept. This one is supposed to be 1 over Qmax. Okay? Just correct this. Okay. So your data, you got 1 over QE against 1 over CE, and then you will get a straight line. So this straight line itself, once you know the slope, okay, the slope is equals to 1 over Qmax KEQ. Okay. And once you know what is the y-intercept, you can calculate what is the Qmax. Okay. So other method includes this one. This is also a linear method, just that the equation form is different. Okay. Same thing with the uncertain method. Okay. You can see yourself, QE equals to Qmax minus 1 over K times QE over CE. This one is your X. This one is your Y. So your intercept will be Qmax. Okay, this one. Uncertain method, this one is your Y. And then, let's see. This one is your X. Okay, so this is your Y-intercept. Okay. So of all the methods that you have, okay, different methods that different people use, okay, determine what is the Qmax and K. There is a problem, right, in terms of the consistency, right? If you look at the literature, you take their data, okay, you use that data, and then you try out to see whether what they do is correct or not. Let's say they are using non-linear regression method. You transform their data into linear method, okay? And sometimes you will find that your linear method compared with your non-linear method, there's a huge discrepancy. From 300, let's say this Limeweaver-Berg method, 300, right? For Qmax. Non-linear give you 370, right? Your equilibrium constant also varies depending on the method that you use. Okay, so what does it mean? Which one is the correct one, right? For your standard deviation, sorry, there should be a point here. Okay. So what does it mean? Okay. It means that the linear method itself is problematic. Okay. Sometimes it's problematic. And if you really want to carry out adsorption study, you need to make sure that the data that you have, they are reliable and they are not just like a few points on, right? Otherwise, if you only have a few points, okay, let's say your isotherm, you only have 5 points or 4 points or less, right? And you convert it into the linear form, and then after that you use it to determine your Q max and K value. There's a very high chance that what you're doing is wrong. It's not correct. Okay? This is due to the big random data error. Okay? Once you convert the data into linear form, you can introduce this kind of error, whereby they will not give you an optimum estimate. So whenever you see a paper that reports using Langmuir model, okay, or any form of a model, okay, the linear form, okay, you have to question. Okay? If you look at the results that they have, they only present 3 or 4 different points, and then they say that the Q value is this and the K value is this. You have to question them. Is what you're doing using linear method reliable? Is the result the same as what you have when you are using the non-linear method? Okay, so you have to be careful when you are doing linearization, especially for some of these, like Langmuir, Monod equation, or Michaelis-Menten. So this all this you usually see them in enzyme, in microbial growth, and so on, right? So you have to be very careful with this. Okay, next one would be the Friedrich isotope, which also very commonly used. Okay? The two very common one, as I said, is the Langmuir and Friedrich isotope, right? It has to be there. Every paper that is seen, definitely they will discuss these two. You cannot miss them. Okay. So this Friedrich isotope is an empirical isotope, which means they are not derived based on a mechanism. Okay. So you have a you have a model, a mathematical model that are derived based on mechanism, and you have one that are derived based on empirical. Okay. So for empirical derivation, okay, let's say this is empirical. Okay, this is empirical. Usually the constant that you have does not have very clear physical meaning. Okay? Which means that you cannot really interpret the values, okay, to a mechanistic in a mechanistic way. Okay, like this now Langmuir, you can say that the K value increase. That means the adsorption tendency is higher. But for the Friedrich isotope, because it's empirical, we cannot say the same thing. Okay? We cannot say that K value increase, which one is higher and so on. Okay? So which means the physical meaning of your Friedrich isotope, they are not clear. Okay? But the good thing is that we can look at the trend. Okay? So for 1/n, so for this case, if 1/n is 1, you can have a straight line. If 1/n is less than 1, you have this form. And 1/n more than 1, you will have something like this. Okay? They are empirical model. Okay? Okay, to estimate this Friedrich isotope, we use linearization. Some people use linearization, okay, to get this form. Okay, this is one way. The other way is directly use this equation. You can use non-linear form. You can use linear form. Okay? But like I said, when you linearize it, you have to be very careful. If you are only using 1 or 2 points of data, you may not get the correct value. And you also need to set a boundary. For Friedrich isotope, the K and N value have to be positive. And that's the boundary. It cannot be negative. Okay? So if you look at this, Langmuir and Friedrich, the most commonly used. Okay? There are also people talking about SIPs isotope, Radish-Peterson isotope, Kahn isotope, and so on. So many different isotopes, BET isotopes. Okay, so all these isotopes, in my point of view, they have their own use case, but some of them are derived for the sake of publication. Okay, so you know when you want to publish something, right, you have to come up with something that is novel or innovative. So what most of these people do when they want to publish paper is they come up with an isotope of their own, okay? So that they can use that isotope to model their adsorption equilibrium. Okay? And then over time, a lot of people started to do these kind of things. Okay, they come up with a name for their own isotope. You can see if you look at the list of isotopes that's available, probably you can find 100 or more than 100 of different names of isotopes. Okay, so one thing that is important is that the Langmuir and Friedrich one is the classical one, the one that most people use. Okay, that's a generally well accepted one. Other than these two, other isotopes, they are just like a additional isotope lah. Okay, so I will not cover all these other isotopes. They have their own interpretation. They have their own use case. Just that I find that some of these isotopes contains a lot of parameters, okay, a lot of constant. So when you have a Langmuir isotope, you have two constant, right? So two constant still acceptable. Okay, for a two parameters system, right? So for Langmuir, you need to know what is your QE, you need to know what is your CE, right? And then from there you determine by fitting into a two parameter, two constant equation. Okay. Some of these equations have more than two constants. For example, if you look at Reddish-Peterson, this one you have three constants, right? Generally, the more constant you have, the better fit you will obtain. This is mathematical, so everyone knows that. As in, if you have four constant, you derive an equation that has four constant. It will fit better than the one with the three constant. So that's why I don't really like this kind of game. Okay? They are playing this game whereby they come up with an equation, and it has more than three constant, and then they say that they fit better than the Langmuir model, which is not really correct lah, in my opinion. Okay, so next one, just want to quickly go through this thermodynamics part. Okay, so thermodynamics can tell us several things in terms of delta G, delta H, and delta S. These are the three things that a lot of people are looking into when they want to study thermodynamics. So this free energy tells us whether that particular reaction is feasible or not. Okay? You can get a negative value, positive value, and each has a different meaning. Okay? So enthalpy tells us about the heat of the system. Okay? If you have chemi-sorption, you probably have more than 100. Okay, depends. Okay, so the other one is entropy. Entropy is to tell us whether it's spontaneous or not spontaneous. So this one, probably you have seen all this symbol in your thermodynamics class. So for your delta G, you can calculate easily once you get the equilibrium constant. This one you can get it from Langmuir model. Okay, Langmuir model, and you can calculate what is your delta G through this equation. Negative R. R is your gas constant. Okay, usually it's 8.3145. E is your temperature. Okay, and from here you will know your delta G. Okay, so relationship between delta G and delta H and delta S, you can calculate everything using this equation. So this is a linear equation whereby you can get the equilibrium constant at different temperature. So you plot this whole thing is your Y, this is your X. Okay, so from the plot of the linear graph, right? From the plot of the linear graph, your intercept will be negative delta H over R, and your slope will be delta S over R. Okay, so in terms of absorption, if it's between 2.1 to 20 kilojoule per mole, it is physical absorption. If it's 80 to 200, it's chemi-sorption. But if it's 63.8, it's between. Okay, that means you have two processes, chemi-sorption and physical absorption. So this is quite common. So last time when I worked with adsorption of phenol, right? Adsorption of phenol using activated carbon. Right? So what I did was I carried out some adsorption process, and then after that I carried out some desorption. Okay? After adsorption, I carry out desorption experiment. Okay? So what I found was that the phenol itself cannot desorb 100% from the activated carbon. Okay? So the reason is because when you have phenol as your pollutant, right, it can undergo two types of adsorption process. One is you can form a pi-pi interaction with your activated carbon to form a physical adsorption. It can also be adsorbed and it can undergo oxidative polymerization reaction, okay, on the surface of the activated carbon, which means that it can have irreversible adsorption. So that's why you can see that activated carbon itself is very complex. It has a lot of functional group, and all these functional group, it can induce physical adsorption, it can induce chemical adsorption. So it's not just like everything will be physical adsorption. Okay? It's always a mix between two, physical and chemical adsorption. Okay? So once chemical adsorption is formed on activated carbon, it's not so good. Okay? Like I said, because you will have the active sites being deactivated. Okay, that means the activated carbon, once I carry out desorption, all the phenol has been dissolved, and then I take the activated carbon, I use it again for adsorption process. And what I found was that the adsorption capacity of the activated carbon drops. Okay? Drops quite a lot. Okay, so chemisorption sometimes is not so desirable, but it still happens. Okay, so just another problem that I want you all to be aware of. Okay, if you look at the ammonia, right? Again, this K value, it has a unit, but this K value has no unit. So what does it mean? What is wrong here? So there's a fundamental explanation to what is wrong here, why there's an inconsistency. Okay, so the second problem that we face when we are doing this kind of calculation and reading through papers is that some people, they use different models to calculate the delta G. Okay, so when you have a different model and you calculate delta G, the answer is different. So some people compare directly, some people just use that use a Langmuir model, some people use their own model, and then they compare directly and say which one is the better one. So this is not really acceptable in my opinion. Okay, so if you want to use a model, okay, to calculate what is the delta G, it has to be the same. And if you using K from different model, they are not comparable. Okay. Okay, last one, just to finish up the absorption kinetics and the last part of our three parts, right? In terms of the absorption thermodynamics, absorption isotherms. Okay, last one would be the kinetics that a lot of people are looking into, and there are a lot of problems with kinetics. Okay, so if you look at the kinetic study of adsorption, you will see that a lot of people are using first order kinetics and second order kinetics. So the two models that people use for adsorption kinetics, they are empirical models, which means no mechanism. They are not derived based on mechanism. Okay, and so far there's not really any successful study that link this first and second order model together. Okay, but of course, if you do some mathematical transformation, right, this is the first order, this is the second order, you will find that eventually they can be linked to the same form. Okay, so that means there's something between these two models, okay, that can be used to describe the adsorption kinetics. So this adsorption kinetic, people work in a reverse way. Usually, when we want to know the kinetics, we derive the mechanism first. So from the mechanism, then we derive the kinetics. But for adsorption case, it has been a very long time. Right? People derive the kinetics first and then try to figure out the mechanism. So this is happening in the reverse way. So I don't know why this is happening like this, but yeah, you know, this one, a lot of people are using the first and second order kinetics because they are able to describe the system relatively well. Okay, and no one knows why. Okay, which means that the K value that you get from this kinetics, they cannot be interpreted that easily. Okay, you cannot say that the K value is larger than another one. Okay, and then that means this is faster. You cannot say that. Okay, because all these are derived empirically, and the K value may not reflect the speed or the rate of adsorption process. Okay, so you have to know that if you want to say that this K value represent the rate of reaction, you have to have a mechanism to back that up, okay, to give it a physical meaning. Otherwise, it will not have any physical meaning. It's just fitting for the sake of fitting to get what you want. Okay, so this one you have to be aware of that. Okay, so if you want to derive it, rate of adsorption, rate of desorption, you can actually use something like a Langmuir model, okay, something like this. And then in the end, if you use the Langmuir kinetics, you will get this form. Okay, whereby this one is the first order, this one is the second order. So that there's a certain link, but the link is not really clear. That's why people have been struggling to figure out what order is this adsorption. Okay? Some people claim second order is better. Some people claim first order is better. Okay? So one of the key problem, okay, when people are talking about which model is better is the way they do it. Okay? So they claim that first order is better than second order, or second order better than first order, usually based on the R square. R square value is whereby you can use it to estimate the goodness of fit. Okay, so if your R square value is 1, which means you have a perfect fit, right? So most of the time when they use first and second order, what they found is that you can have like 0.995, 0.990, 0.985. They're very, very close to each other. Okay, you can see here from 0 order up to 4th order, first order up to 4th order, right? R square is so close together. It's impossible to tell which order is the kinetics, right? So that's why one of the problem is that the R to be used as a goodness of fit is not really significant. Okay? You have to have a different approach. And one of the good approach is to use something else like the root mean square error or relative goodness. So this one you have to be aware of when you are comparing two different model. Okay? Not just apply for kinetics, but also apply for every single thing that you do when you are fitting your model. Okay, okay, I'm going to talk about some application. Okay, so that one I have briefly talked about adsorption isotherm, adsorption kinetics, and also thermodynamics. So now we want to look into the application. So there are two types of different application that people can use. One is the activated carbon column system, okay, which means you pack in a column. And once you pack it in a column, then you flow the water through the column. So this is a continuous system. Okay. The other way is a batch system, whereby you just need to introduce the activated carbon into the water for adsorption process to happen. Okay. Both has been applied to treat real wastewater. Okay. Batch system and also the column system. So for column system, usually it's more practical but it's relatively more complex because there are a lot of parameters that you need to adjust. Okay. This is how a column system looks like. Okay. You pack it, you pack the GAC. Most of the time it's GAC. Reason is because of the size. You cannot use PAC. If you use PAC, water will not be able to flow through it. Okay, you will clog the system. That's why people use GAC, granular activated carbon. Okay? That's why we use that. And some innovation that you can do, for example, for this case, is to impregnate silver nanoparticles on the activated carbon. Okay, so when they do this kind of impregnation, when they want to treat E. coli, when E. coli goes into the activated carbon, when it's in contact with the silver, it will be deactivated. Okay, so this kind of column system is very versatile. You can modify the activated carbon, and it depends on what you want to use it for. Okay, if you want to use it for E. coli deactivation, then you can put some silver. But for this system, just to share with you, for this system, if you know that someone do this kind of study, okay, and try to treat the water using E. coli through this AG and AC column, I will probably not want to drink this water because from my experience, silver probably will leach out and it will go to the water here. So they probably have to do another additional microfiltration before they can allow people to drink this water. Okay, so to describe the adsorption process, you look at this. We use the breakthrough curve. Okay, so for continuous system, usually we use the breakthrough curve, whereby to look at this curve, right? Initially, you have this is the outlet concentration. Initially, you have a fat. There's nothing here. Okay, which means that the outlet is very clean. There's no pollutant. Okay, then after that, you will start to detect pollutant. Okay, that means a warning sign already. Okay, and then there will be a breakpoint depending on where you define the breakpoint as. Okay, you can define it here, or anywhere. Okay, and once it reach complete exhaustion, okay, which means that your inlet and outlet concentration is the same. Okay. Okay, I have a question. Okay. So do we need to consider the packing density of AC in the column? Definitely yes. Packing density is one of the important parameters that you have to look at. Okay, so packing density to determine what packing density that you want, it has to be consistent with what operating system you want. The flow rate, okay, flow rate is one of the important parameters. And then you need to look at the size of the GAC, the pollutant treatment, the lifespan, okay, and so on. There are a lot of factors to consider. Okay, and yes, you need to consider the packing density. Okay? And to design the column, right, normally they will put something here, some bigger particles here. Okay, so that you have a more even flow when you go up. Another one is any alternative to substitute silver for biofouling prevention in the column. Well, if you look at metals, okay, there are two important metals that have disinfection ability. One is silver nanoparticles. The other one is copper. Okay, copper nanoparticles. You don't want to have copper because copper is more toxic, very toxic, and it leaks out very easily at different pH. If you have pH, acidic pH, copper will leach out. So alternative to replace substitute silver, if you talk about the metal one, the nanoparticles, I still think that silver will be the better choice. Okay, but just that when you want to do this kind of disinfection, you have to control the silver concentration. Okay, in fact, to tell you that this silver, right, some water filtration system, the small scale one, the one that you bring at home, right, they have silver, you know, they have silver as one of their disinfectant. Okay, so you flow the water through and then it goes through the silver part. Okay, just that when you want to design it, you have to consider the leaching problem. Okay, that's the thing. Okay. The other one is a mechanism. Okay, are there any? Okay, how is the mechanism of bacterial adsorption? Okay, in my experience, adsorption of bacteria is not possible. Quite impossible to adsorb. Okay, living bacteria, they tend, when you have GAC, right? When you have bacteria attached to a GAC, they tend to form biofilm, okay, which means that they colonize the activated carbon. That's why we have something called the BAC system, biological activated carbon system, whereby they combine biological system with activated carbon, which means that you have a column, and each column has a GAC, right? This GAC, it has a layer of bacteria on it. So this is BAC. You can Google BAC, biological activated carbon. You'll find that there are thousands of papers talking about this. Okay, and adsorption of living bacteria, impossible. It will form biofilm. Okay? It will definitely form biofilm. And usually for this kind of system, when you deactivate it using silver, then the bacteria will be retended. Okay, retended, not adsorbed. Okay? You look at the size of the bacteria itself, and you compare it to the size of the macropore. Right? Bacteria size sometimes is larger than the macropore size. Okay, and if it's larger than the macropore size, then definitely it will not be adsorbed. Okay, so this column can only retain it. Okay, retain it like a filtration. So sometimes the dead E. coli, for this case, it will go to the disinfected water. Okay, so you cannot really remove it by adsorption. Okay, next one is the regeneration. Okay, once you have activated carbon, it's a process of concentrating the pollutant on the surface, right? So once the surface has been filled with the pollutant, then this activated carbon cannot be used anymore. So you have to do regeneration, right? So regeneration you can carry out using several ways: thermal regeneration, chemical regeneration, or biological regeneration, right? Or there are many ways to do it. Okay, so the common one for the large scale regeneration is using thermal regeneration. Okay? Thermal regeneration, you heat up to a certain temperature under oxygen limiting condition. Then the pores will start to be regenerated. Okay? You can actually destroy the adsorbent through, you can actually destroy the adsorbate through this process. Okay? So the adsorbed species will be destroyed under heat, and you can recover partial adsorption capacity. Okay? But while doing this, definitely some of the activated carbon will be lost, okay, because of attrition. And when you burn it, right, some of the activated carbon may be burned, okay, to some extent. So I'm familiar with two forms of regeneration because I did some study on this using chemical regeneration, using AOP, okay, and also biological regeneration. In fact, my master's degree, I work on biological regeneration of activated carbon, which means I'm using microorganism. Okay? I culture the microorganism, and then I use them to regenerate the activated carbon. Okay? But after some time working in regenerating activated carbon, okay, a very important question arises. Do we need adsorbent regeneration? Okay, so so one of the reasons why this question is important is because now if you look at 20, 30 years ago, activated carbon is expensive, right? So because it's expensive, it's worth regenerating. So today, by today's standard, right, activated carbon is very, very cheap. So that means we don't really need to regenerate the activated carbon. In fact, we only need to replace it. Okay? We can replace it easily. And the replacement cost is sometimes cheaper than when you want to regenerate it. That's why now the question of whether we need to regenerate, is it necessary or not? So two things that you need to consider is the cost and the environmental footprint. And the cost is always the important one. Okay? How expensive is regeneration compared to buying a new one? Right? This is, like I said, regeneration is important, but usually in industry, when we want to regenerate, you recover what has been absorbed. For example, if you are in the industry whereby you are working with gold, right? Then that's the point where you can talk about regeneration, because when you regenerate your adsorbent, you take adsorbent to adsorb gold. Let's say you generate wastewater containing gold. You take adsorbent, you recover the gold, okay? And then you take this spent adsorbent, you regenerate the spent adsorbent by recovering the gold, right? Then it is good because you actually get something out of it. But if you are looking into the wastewater treatment, right, it's not worth regenerating an adsorbent anymore. Okay, that's why I don't really work on this regeneration of activated carbon anymore because of this reason. Okay. So I want to share some experience. This is a site visit that I have in Mannheim. This is in Germany. So there's this activated. They are using activated carbon treatment to remove their micropollutants. Okay, so what they have is a wastewater from industrial wastewater and municipal wastewater. So they blend these two wastewater together, right? And then they flow it to the wastewater treatment plant. Okay, so this wastewater treatment plant have about 725K capacity. Okay? It is for almost 1 million people. Okay? And in their wastewater, they are detected micropollutants. That's why the government there, the local government there, is trying to find a way so that they can remove the micropollutants. Right? So one of the proposed technology that is quite effective is the activated carbon, right? Because it's reliable and it doesn't really lead to the byproduct. Okay, so as you know, if they choose ozonation, it will cause formation of byproduct. So if they use activated carbon, it's less likely to give you byproduct. Okay, so what they have is that first, water that flows through undergoes biological treatment, which is the secondary treatment. Okay, so after biological treatment, which covers nitrification, denitrification, and then it goes to the clarifier to remove those, the sludge, right? Then they will channel the water into an activated carbon tank. Okay, this tank contains activated carbon. So they are doing it like a batch system, right? It's not a column, but it's more like a batch addition of activated carbon. So what they did was they pump in this activated carbon using this pipe to the water, right? So continuously, the activated carbon will be introduced to the water, okay? Along with certain coagulant. Okay, so the powder they are using powdered activated carbon. Okay, and after this activated carbon treatment, it will go to a sedimentation tank. Okay, whereby activated carbon added with coagulant, they will bind together and they will settle down. Okay, so once you settle down, you will get quite a clean water. Okay, but it's not enough okay? Because activated carbon cannot 100% remove all the micropollutant. So they need to channel it to another treatment system using filtration. Okay? So they use filtration using anthracite, okay, and sand, and to remove all those additional things like particles, PAC particles, and so on. Okay, and in fact, after going through activated carbon filtration system, they managed to remove 80 to 90% of the micropollutants. Okay, and then they discharge this to the Rhine River. Okay, so look at the water quality before discharge is relatively clean. Okay, judging from the color. Okay, so they control everything in the control room, which is quite modern. Today we can control everything using computer. Just press a button. If there's any discrepancy, or maybe if there's any change, like for example, wastewater flowing in, the pH is different from what they want, they can just press a button to shut the water, okay? So that it won't flow into the biological treatment system and contaminate the water and affect the microorganism. Okay. Okay, so I have a question. How was the adsorbent recovery obtained via chemical and biological regeneration? Okay, so for chemical, okay, usually this is how we measure it. So for chemical and biological method, right? First thing we do is we saturate the adsorbent with the pollutant. Okay, let's say the adsorption capacity is 100 milligram per gram, right? So we saturate it with 100 milligram per gram, and then after that, we take this spent, we call it as spent adsorbent, right? And we introduce, let's say if we are using chemical method, we introduce a certain chemical into the into a solution of that spent active carbon. Maybe I just draw it here. Okay, so let's say we have this a lot of this spent. Okay, this is a solution. Okay, we put it in water. This one is your AC spent AC lah. Okay, you have already saturated with the pollutant. So I add chemicals, okay? Or maybe if you are using biological regeneration, you add microorganism. Okay, then what will happen is that the microorganism will be able to consume the surface pollutant. Okay, there are many mechanisms, okay, for this kind of things to happen. If you are talking about chemical regeneration, let's say for my case, the one that I worked with previously, I'm using a certain chemical to generate radicals. Okay, so these radicals will attack the pollutant. So that's the mechanism of how it happens. Okay? But if you are using microorganism, you will see that there are two mechanisms that can happen. First mechanism is that the microorganism, okay, can somehow attach to the surface of your adsorbent and then secrete enzyme into the pores. Okay, and when it goes into the pores, then this enzyme will be able to somehow transform the pollutant into other form and effectively mineralizing the pollutant. The other way is that we have something called a desorption equilibrium. Okay, so when we take the adsorbent, we add into the solution, right? So some of the physically attached pollutant, it will tend to leach out from the adsorbent, because it will have to establish a new equilibrium between the solution and the adsorbent. So when you have a new equilibrium is established, that means there will be some of these pollutant leach out that can be consumed by the microorganism. So microorganism will keep consuming this pollutant, and the pollutant will keep dissolved to establish new equilibrium. So this will keep happening until a point where there's no pollutant able to dissolve anymore. So once you have this kind of process being happening, right? And let's say initially you have 100 milligram per gram, right? After you carry out this process, okay, you contact the spent adsorbent with microorganism, and then the microorganism consume, let's say, half of this pollutant. Then the capacity could probably become 50 milligram per gram, right? So you take this 50 milligram per gram, right? This means that you have already regenerated 50% of the active sites. Okay, so this is how we look at the quantification, how much has been regenerated. Okay, so once you regenerate, you take out the adsorbent from the solution, okay, and then you dry it, and you can reuse it again. And this is but of course, you have to be careful when you're dealing with biological regeneration, because biological regeneration, you tend to have microorganisms. So if you are regenerating it for use in a water filter, okay, drinking water filter, you cannot use biological regeneration, because you will tend to contaminate your filter with microorganisms. Okay. So in terms of the rate of regeneration, if you compare chemical, biological, and thermal, right, the fastest one will be the thermal regeneration. Okay. It's the fastest regeneration method, because you need to heat up, and once you heat it up to a certain extent, then you are okay. You already regenerate it, right? But chemical one, you have to add chemical into the system and allow the chemical to react, right? And to some extent, sometimes you can have some waste. Okay, waste during the process, right? That's also will contribute to additional cost. For biological system, it's the slowest. It's the slowest, and I consider it's the less efficient one compared to the 3 other regeneration methods. Because microorganism, when you want to use it to biodegrade the pollutant, it takes time for them to grow and for them to really consume it. And sometimes microorganisms, they tend to form biofilm on the surface, which is what could be undesirable. Okay. Okay, so moving on, I want to show you what are the techniques that people use to prepare adsorbent. Okay, and then I want to discuss a bit on how we can characterize the adsorbent, and finally to talk about what are the things that you have to do so that you can publish in a high impact factor journal, if that's what your goal is about. Okay, to publish. So I would say that adsorption is okay. Let's look at the preparation first. Okay, so to prepare the adsorbent, right, we have to consider quite a number of things. Example, the type of adsorbent that you want to prepare. You can have zeolite, you can have activated carbon, boron nitride, xylene, or any different things, okay? Different materials. Okay? You have to consider the type, you have to consider the nature of your pollutant. Okay? Whether your pollutant is hydrophilic, okay, or hydrophobic. You have to consider you want to prepare it for continuous system, okay, which means column. If it's column, you have to prepare in the larger size. If it's batch, then you can prepare in the powdered form. You also need to look at the cost and resources. Okay, so all these, they are quite critical. But for this part, I think I have about 20 to 30 minutes left. So I'm going to talk about only how to prepare activated carbon from bio waste. Okay? Because I know this is of interest to many people, okay? Especially in Indonesia and Malaysia, whereby we have a lot of biomass waste. Right? So this biomass waste, we can convert it into adsorbent. Okay? And if you look at the scientific publication, okay, you type adsorbent from biomass waste, you can see thousands of articles, right, been published already. There are so many articles. But if you want to prepare a high impact factor journal article to be published, okay, there's a trick to do it. Okay, it's not like so many people doing it and so many people got rejected, and it's already saturated. It's not really like that. It's just a matter of whether you target and address the correct question or not. Okay, so this is what I'm going to share with you. What are the questions that people are still interested to look at when you are doing adsorption study and you are using biomass waste as your precursor? So general preparation of biomass waste to activated carbon is given here in this very simple schematics. Okay, so you always start with biomass. Right? Biomass means anything that you can find that is organic. Let's say you go to your kitchen, you take orange, right? You eat the orange and you peel the orange first, right? So the orange peel itself is a bio waste that can be converted into adsorbent. Okay? And if you don't convert it into adsorbent, of course, you will throw it away, right? You will end up in the landfill and you will contaminate the environment. So this biomass waste, in order to convert it into adsorbent, we have to do certain things. For example, let's say orange peel. Right? First thing you have to do is you have to crush it and then dry it. Okay? Once it's dry, you can make it into very small form. Maybe you can blend it. Okay? Use a blender to blend it into a very, very small size. Okay? And then you sieve it to get the size that you want. Okay? So this is very general approach. Anything you can do. But when you want to select the biomass, right, try to select one with higher carbon content. Because if you select one with like less carbon content, like silica, right? Silica, rice husk, okay, rice husk. Rice husk contain a lot of silica, right? So if you want to use silica and convert into adsorbent, I find that it's relatively harder to get high surface area adsorbent compared to when you use something that contains a lot of carbon. For example, sawdust. Okay, sawdust has a lot of carbon. It is lignocellulosic, and you can easily convert it into high surface area adsorbent. Okay. Another one is the coconut shell. Coconut shell is also very easily converted to adsorbent. And in fact, some people consider coconut shell as one of the high quality activated carbon precursor. Okay, so this is biomass. Once you have it in your desired size, you can carry out these two things. One is dry carbonization. okay, which means you heat it under inert condition, okay, up to a certain temperature, maybe 300 or 400, usually 400 or 500, around 400. You will convert it into black color powder. Okay, so this black color powder is your biochar. Okay. If you want to use another approach, which means using hydrothermal carbonization, that means you have a hydrothermal reactor, right? You put the biomass inside along with water, right? And then you put it in the oven, okay? Maybe around 180 to 250 degrees Celsius. All the biomass will be converted into something called the hydrochar. Okay? It's also black in color. And we call it differently. Okay? Biochar and hydrochar is because certain characteristics between these two is different. Okay? Usually, hydrochar in general have more OH functional group. Okay? And it depends on what precursor you use. Okay? Precursor is very important. Okay? So after you have obtained this hydrochar and biochar, right? You want to turn it into activated carbon. Okay, like I remember just now there's a question asking about how to make it high surface area. So this is how we do it. We do certain activation. Okay, and of course activation to work, in order for it to work, it will also have to depend on the precursor that you use. Okay, so the precursor that you use, if it's like I said, something that contains a lot of inorganic materials, okay, like rice husk, maybe the activation method may not work as well as when you have all carbon. Okay, so there are two types of activation: physical activation and chemical activation. So physical activation means that you are using heat. Okay, most of the time heat. You heat it up to a certain temperature, maybe 800 degrees Celsius or 1000 degrees Celsius. Okay, and you flow it with inert gas. Okay, sometimes carbon dioxide, sometimes steam. Okay, so these two are the common one: carbon dioxide and steam. They can generate porosity for your activated carbon. Okay, so when you have a porosity being generated, that means your surface area will increase significantly. Okay, so this is activation approach that physical activation approach that people usually use. So this is how it looks like in terms of preparation. Right, you have the sample. Right, you flow two gas. Let's say this one you use CO2. You flow it together into the this chamber and you heat it up. Okay, so the temperature that you use to heat up, you can use 800, you can use 900, you can use 1000, depending on the setup of your furnace. But there's a drawback. Drawback is that higher temperature you use, the lower product yield you will have. Okay? But higher temperature often will result in better adsorbent. Okay, so there's a optimized point. You have to determine yourself. Okay, is it acceptable for me? If you heat up to 1000, you get smaller yield, okay, compared to when you heat up to 800. Okay, so if you want to have better adsorbent, you can even heat up to 1500. Okay, but just that the problem is the yield. Okay, sometimes 100% you put in, you may only get 2% yield, very low. Okay, that's not acceptable given the energy that you put in. Okay. Next one is the chemical activation. Okay, so chemical activation generally means that you are using certain chemicals. Most of the time is acid or base. Okay, so that you can induce the formation of pores. Okay, so this strategy, some people consider it better compared to when you use only physical activation. Okay, so how this works is that when you have let's say potassium hydroxide, so you mix this potassium hydroxide, okay, together with your biochar or hydrochar. Okay. There are a lot of ways to mix it. One way is that you prepare a solution of potassium hydroxide, and then you add in your activated carbon, your biochar, okay, your biochar and a solution of KOH. You mix them together, and then you dry it. So once it's dry, you will get a perfect mixture of KOH and biochar. You take this mixture, you heat it up to maybe 300 to 500 degrees Celsius. Then you will end up with activated carbon. Okay, so some people use different chemicals depending on what you want. Some people use zinc chloride, some people use phosphoric acid. Okay, they have different application. Okay? In fact, some people also use iron chloride. Okay? So iron chloride, I personally don't like to use metal base, because when you use metal based chemicals, you will get activated carbon, but with metal attached to it. Okay, especially heavy metals. Like iron, right? If you use iron, then your activated carbon product will have a lot of Fe. So when you want to apply in wastewater or water, this Fe they will tend to leach out. So when you have leaching, that means you will have this secondary pollution issue. Okay, that's why I don't really like to use chemical activation based on metal. Okay. So just to show you some comparison of a different activation approach that has been done by many people. Some people use nitric acid, some use phosphoric acid, and so on. Okay, you can see there are quite a lot of the different chemicals, and all these chemicals, it has its own mechanism and function. For example, KOH, it can react with carbon and form the pores. Okay. So in terms of selection, okay, selection of which one is better, I would say that depends again on your application. Chemical activation, quite a number of researchers saying that it's better because it has lower energy requirement, and it can help in getting better porosity compared to when you have physical activation. But there are people who are doing multi-stage activation, okay, which means that you're not limited to a single stage. Okay, to choose whether you want physical only or chemical only. You can actually have both together, physical and chemical activation. But most of the time, okay, 2 or 3 step activation is only fancy for publication. Okay, people want to publish a paper, and then they tell you that okay, you do 4-step activation is better than 3-step activation, and so on. Okay, most of the time people do 2-step activation, 3-step activation is just for publication. Okay. Whether there's any real application of the 3 or 4-step, it remains to be tested. And reason why we usually don't apply 2 or 3-step is because for real application is because of the cost. Okay? One thing is the cost of doing this multiple step activation. Second thing is that it's not necessary. Okay? Not necessary to do all these several steps activation because it consumes a lot of energy. Okay? And often, if you get the final activated carbon, you can achieve it with optimized condition through 1-step process. So that's my opinion. Okay. So there are many articles that talk about this comparison. You can look through it. One of it is this one. This has been published in Microporous and Mesoporous Materials Journal, comparing chemical and physical activation. Of course, this journal is saying that chemical activation is better compared to physical activation, okay, because it produces better mechanical properties and so on. Okay, so when the journal claim that they have this method and it's better than others, you cannot just blindly believe it. Sometimes you have to really look at it and what they have done, because a lot of people claim a lot of different things. So we have to be very skeptical. Okay, just to show you, this is just to show you that there are studies that compares between chemicals and physical activation. Okay. Okay, that's about it for the preparation. And in terms of characterization, we have many types of characterization technique. Yeah, I'll briefly go through this. Yeah, I'll give you an example of how we can use absorption study and we can characterize it. Okay, so this characterization, we use SEM, TM. They are basically has been covered in the membrane part. Okay, in general, they review data about the adsorption process itself. So I have seen a question. I would like to control mesoporous microchemical activation. Is there any special rules in terms of activation condition agent? Well, controller, if you are talking about activated carbon, it's very difficult to control activated carbon. If inorganic, yes, mesoporous materials such as zeolite, you can control it very easily. But if you are controlling activated carbon, okay, so for activated carbon, the porosity control, let me see, porosity, so far I'm not aware of any study that really is able to tune the porosity of that activated carbon, okay, controlling the mesopores, okay. But micropore you can easily control, because every time you prepare using, like, let's say chemical activation using KOH, potassium hydroxide, you will have a lot of micropore being formed. Okay, but if you really want to specifically control that activated carbon just to have mesopores, okay, there's no micropore in it, then that's very challenging. I don't think there's any study that really successfully control only micropore formation in activated carbon. Okay, but if micropore is easier, okay, because the micropore is always formed. Okay, when you, regardless of the agent that you use, it will always form. So in terms of the parameters that will affect the pore formation, if chemical activation, it will, yes, you're right, in terms of the agent itself, it will cause you can control it. Just that if you look at the mechanism of how a certain chemical react, you will see that it's impossible to control it in terms of getting it into mesopores or micropores. For example, KOH, it reacts with carbon. So carbon reaction directly, just like that, is very difficult to get it. Okay, so I will go through, I will check through if there's any article I will share with you all. Okay? So just to go through another, yeah. Okay, for this one, adsorption capacity, some people characterize based on adsorption capacity, and sometimes you can see manufacturer, they will include iodine number, phenol number, and molasses number. So all these have their own meaning. Okay, you can go through here. So I want to introduce you to why we do certain characterization. So this is one of the articles that I published last year. So this is on developing boron nitride as one of the adsorbent. So what I did was I used this boron nitride to remove heavy metals. So I prepare this boron nitride at different temperature, okay, from 700 to 100, 1050. Okay, and then after that I use a pyrolysis method. Okay, this one I use a pyrolysis method. I mix urea and I mix boric acid together, okay, and heat it up to that temperature. And then after that, I do characterization. So I did certain characterization. For example, first characterization I did was using the XRD. So what's the reason why we want to have the XRD? first thing is to confirm what you have. Okay, so I did this adsorbent. Okay, I prepared, and then after getting the XRD, and I know that I get boron nitride. Okay? After getting the XRD pattern and compare with the library, okay? I know these materials contains these two main things, which is the same as the peak that you will have in boron nitride. That's why I can say that my synthesis has been successful. So for everything that you do, you have to confirm it, right? But of course, for this case, right, this one, I have certain peak here, okay, certain peak, the 750 temperature. This reflects the temperature. 750, it means that I have additional things inside. Besides boron nitride, I also have something else, okay, in my adsorbent. Okay, so the next thing I did was to look into the FTIR. Okay, so this FTIR tells me about the functional group. Okay? It's important because I can look at the whether the functional group is effective in telling me what I have is useful for my adsorption study. And then the last one is the this one, okay? SEM and EDX. So SEM and EDX generally tells me about my shape of my adsorbent, okay, whether it's porous or not. Clearly, you can see that this is not porous, right? It's just like a particle-like shape. But the good thing is that I can see that the distribution of my boron and the distribution of my nitrogen, they are evenly distributed. Okay, here and here. So which means that this particular adsorbent that I have consists of boron and nitrogen. Okay. And also look at the XPS to tell me about the surface configuration. Okay, how boron is bonded. So from the XPS, I also look at I also detected this boron being binded with oxygen. Okay, so by right, you should not have know that there's oxygen on the surface. But after doing XPS, then you can see that the surface itself contains oxygen. So what does it mean? It means that my surface have OH functional group. So you have BN, right? So this boron itself on the surface, it can bind with an OH. And then you can look at the nitrogen, right? Nitrogen also have O, which means it could also have an OH on the surface. Okay, so this is how we look at the XPS. So I think I will stop here. I will continue again next week on the additional details, because I know the time is already up. Yeah, over already. So sorry for that. I will continue again next week on this one. So, and I promise next week I will give more time for you all to ask questions. Okay, so maybe I will spend about 20 minutes time next week to accept. To answer all your questions. Okay. Yeah.
Okay, Dr. Wenda, thank you very much. Very interesting. Yeah, many questions rises during the during the lectures, and this is, I guess, a very fundamental knowledge for our students because some of our students taking this topic for their final project, Dr. Wenda. So it would be very, it would be, it would also very useful, for them as the the basic information how to prepare the good adsorbent, especially for water treatment applications. And I do believe still some questions from the student, and actually regarding to the characterization, maybe next week you can also describe in more detail, Dr. Wenda, due to the, for example, determination of iodine number and so on. It would be also very great information for our students. And to all participants, since we are over by the time, if you still have any question, just quick question, I can provide you 1 or 2 minutes. Okay, in that case, because usually after this, the student have other class. Then they have to prepare for moving to other class. So Dr. Wenda, thank you very much for very, systematic lecture today. And in our curriculum, actually we separately, deliver the content, for example, regarding to the kinetic of adsorption and thermodynamic of adsorption, we deliver in physical chemistry courses.
Okay.
And regarding to the material preparations, we offer in the material and characterization courses. But here, you can blend it together comprehensively. So it's, I guess, very good approaches, for our students to get the good, understanding regarding to adsorption topic. Okay, to all students and participants, wish you a great day. And is there any assignment for today? For this
Oh
week?
yeah, I forgot to mention this. I just quickly go through this. I have one assignment. You can go to the tablet. So this will be what we will do for the coming weeks. So for week 4, we have an essay assignment on adsorption, whereby you will need to submit on week 6. Week 6 means that 2 weeks time. Okay. So this will be for me. I will grade you as 20%. The poster one is 10%. And next week, I will give you an assignment consists of a lot of questions, okay, for the students to answer. And then week 6, we have like a presentation assignment, whereby students will have to upload a video of a presentation. You can, it depends. You can do it in a group or you can do it in the individually. I will give you more details on week 6. So for now, essay assignment, all the instructions and details are at the Padlet website. The Padlet, you remember the Padlet site where I upload all my notes? It's all there, so you can have a look at that. If you have any problem or any question, you can just type at the comment section. I will reply to that. Okay, that's all from me.
Okay, all right. So for all students, please kindly refer the link that provided by Dr. Wenda for doing your SI assignment. Very good luck. And maybe if you still have any, inquiry or question due to the assignment, please kindly contact Dr. Wenda, or even though contact me. Then later on I can direct the question to Dr. Wenda. So I guess we can close the session for today's lecture. So thank you so much, Dr. Wenda, for always supporting us for this lecture, and see you again next week. Wish you a great day. Okay, thank you so much. Thank you so much. Okay, see you. And then to all participants, please kindly, respond the attendance link, And also please kindly check the link for your assignment and for the instructions that been provided by Dr. Wenda. Very good luck for your assignment. We do hope your best. For this assignment, for this second assignment. There are 20% for your final rate. For this lecture. Okay. Still some students filling the assignment. If you already complete, put your response, then I will close this lecture.
Okay.
Okay. Okay, see you everyone. See you, Dr. Wenda. Wish you a great day. Okay, thank you so much. Terima kasih semuanya untuk partisipan terkait perkuliahan, assignment perkuliahan untuk mahasiswa yang directly join di perkuliahan ini, dan juga untuk yang credit earning. Mohon di refer untuk assignment yang kedua di link yang Dr. Wenda berikan. Mungkin nanti Ibu Mita juga bisa reminder di Google Classroom untuk memastikan mahasiswa bisa attract informasi untuk keperluan assignment-nya Semoga semuanya sehat selalu. Wish you a great day. Saya tutup perkuliahan ini dengan bacaan hamdalah. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih semuanya.